Disruptive technologies have been a rule throughout human history rather than an exception. Examples include the use of fire for cooking, heating, protection, and ultimately manufacturing of metallic objects for tools and jewelry and various other things. Domestication of animals to drag things around, later combined with the invention of the wheel, put oxen and horses to work. Steam engines come along, providing advances that put horses and canals largely out of work as they powered higher speed trains and ultimately factory sweatshops. Once the forests near industrial centers were destroyed, people turned to coal for steam production. Soon steam was used to generate electricity to replace steam engines with electric engines. As electrical power became more and more important, not only for factories but for daily home life, coal continued to power the world. It was a filthy, dangerous world that was still killing thousands of people in modern countries until this very day. In 1847, men and boys with torches led people through the thick smog of London. In 1873, hundreds of people died, and many times that were sickened in London from coal-fired smog. Cattle at the market collapsed and died gasping for breath. The Great London Smog of 1952 killed about 12,000 people and hospitalized somewhere between 150 and 200,000 people between December 5th and December 9th of that year, 1952. A cold snap caused people to burn more coal beneath an anticyclone that trapped the pollution. It was a combination of meteorology and out-of-control coal burning that led to that disaster. And ultimately, that, in turn, led to the Clean Air Act. The story of using the Battersea Coal Power Plant is another story of meteorology and coal power coming together in a disastrous way in London. Pink Floyd had this giant pig built, filled with helium. They hired marksmen or snipers to shoot it down in case something went wrong. The pig broke loose from its mooring and floated off into the countryside over Heathrow Airport, one of the largest airports in the world, disrupting all air traffic for a time. Ultimately landing in a farmer's field, the farmer called and complained that the pig was terrifying his cows. Somebody had to come and do something about it. It's not one of their best albums either. Here in Saskatchewan, in the year 2021, we still rely on coal to generate our electricity. This lecture is produced using coal power, for instance. In geological terms, we're talking about taking carbon dioxide that was slowly fixed as organic matter, sometimes hundreds of millions of years ago, and converting it instantaneously back into atmospheric carbon dioxide by burning it. During the COVID-19 outbreak, we saw the skies of India and China clear quickly and dramatically as the modern world shut down. A transition to a nuclear fission-powered world hasn't taken place as of yet, in spite of all the promises. It's becoming decreasingly likely that will happen anytime soon. Earthbound nuclear fusion, you say? We'll talk about that in a bit, but first let's talk about the nuclear fusion occurring within the sun. On December 14, 1900, Max Planck introduced us to a very simple yet somehow unsettling concept that light must carry energy in discrete quantities. Those quantities must be units of basic energy. Albert Einstein took this idea, and in 1905, when he discussed the photoelectric effect, he began by shining ultraviolet light on the surface of metal. When he did this, he was able to detect electrons being emitted from the surface. Einstein explained this as if the energy in light comes in bundles, then one can think of light as containing tiny lumps or photons. When these photons strike a metal surface, they act like billiard balls, transferring energy to electrons, which become dislodged from their parent atoms. Once they're free, the electrons can move along the metal, or they can get ejected from the surface. This is ultimately going to become the photoelectric effect that we use to this day in our solar panels, our solar photovoltaic panels. Thus, the particle theory of light was back. The quantum theory of light, the idea that light exists as tiny packets or particles called photons, slowly began to evolve. Our understanding of the physical world would never be the same again. The sun is a large fusion reactor. 100,000 years ago, during a previous ice age or a previous glacial period, photons were created in the nuclear reactions within the core of the sun. They ping-pong or bounce around for 100,000 years before breaking through to the surface into the solar photosphere, something we can see. And then they begin their journey towards the Earth, which takes about 8 minutes. So when you go outside, if it's light out, natural light that is, the photons that are striking you can be hundreds of thousands of years old. They've been bouncing around inside the sun for 100,000 years. The photovoltaic effect was first experimentally demonstrated by the French physicist Edmond Becquerel. In 1839, at the age of 19, he developed the first photovoltaic cell in his father's laboratory. Stepping ahead to 1883, Charles Fritz built the first solid-state photovoltaic cell by coating the semiconductor selenium with a thin layer of gold to form the junctions. His device was about 1% efficient. In 1954, Bell Laboratories developed the first commercial solar cell. In 1958, solar cells were used in the Vanguard 1 satellites. Since the 1960s, solar cells have been the power source of choice for all Earth-orbiting satellites. By 1971, solar cells had decreased in cost to about $100 per watt. Following the 1973 oil crisis, oil companies started to use their higher profits to buy or develop solar firms. And for many decades, they were the largest producers of solar technology. Companies such as Exxon, Shell, Arco, and Amoco, ultimately purchased by BP, as well as Mobil, all had major solar divisions during the 1970s and 1980s. Adjusting for inflation, it cost about $96 per watt for a solar module in the mid-1970s. Improvements in production and a large boost in production have brought that figure down by more than 99% to around 30 cents per watt in 2018, as low as 20 cents per watt in 2020. Now, Swanson's law states that solar cell prices fall 20% for every doubling of industry capacity. As of the year 2018, large commercial arrays could be built at below $1 a watt, fully commissioned and ready to go. Now, we see Swanson's law here. Again, the observation that the price of solar voltaic modules tends to drop 20% for every doubling of cumulative shipped volume. At present rates, costs go down about 75% every 10 years. During the 1990s, polysilicon or polycrystalline cells became increasingly popular. These cells are somewhat less efficient than monocrystalline cells, but they're grown in large vats, reducing costs. By the mid-2000s, polycrystalline cells dominate the low-cost panel market, but more recently, monocrystalline cells have become more popular. Reduction in the amount of silicon used in modern cells continues to reduce prices further. In 2021, crystalline silicon panels dominate the global markets, mostly manufactured in China and Taiwan. Solar PV is growing fastest in Asia, with China and Japan currently accounting for half of all worldwide deployment. Globally, installed PV capacity reached at least 300 gigawatts in 2016 and grew to supply 1.3% of the global power in 2016. It was anticipated that electricity from PV will be competitive with wholesale electricity costs all across Europe, and that the energy payback time of crystalline silica can be reduced to below 0.5 years by 2020, so 6 months to pay off your system. Falling costs are considered to be one of the biggest factors in the rapid growth of renewable energy, with the cost of solar voltaic electricity falling by 85% between 2010 and 2021. By 2019, solar cells accounted for about 3% of the world's electricity generation. Research on LED TV screens is similar to, and therefore a benefit to, the solar cell industry. An LED works kind of in the opposite way that a solar cell works. That's a bit of a simplification, but close enough for our purposes. LEDs push electrons through the p-n junction to generate light. Solar cells use light to push electrons through a circuit or battery. Now, one of our problems is there are limits to how many electrons can be pushed in a given semiconductor. Solar cell efficiencies of laboratory-scale devices using different materials have increased from 3.8% in 2009 to 25.5% in 2020. Essentially, by using what are called perovskites, we can combine silicon PV with perovskite layers to harvest other useful wavelengths of light. Perovskite solar cells, therefore, have been the fastest growing solar technology as of 2016. There's a potential for achieving even higher efficiencies and very low production costs, making these perovskite cells commercially attractive. One of the big problems remaining includes their short and long-term stability. Multi-junction solar cells are capable of a higher power conversion efficiency, PCE, increasing the threshold beyond the thermodynamic maximum set by the Shockley-Cuissier theoretical limit for single-junction cells, which is about 30.1%. We don't expect those cells to increase much in efficiency, So we have to use different technology to get beyond that 30% efficiency limit. Just like greenhouse gases have different sensitivities to different wavelengths of light, solar cells can have different wavelength sensitivities. By having multiple band gaps capturing multiple wavelengths in a single cell, we can prevent the loss of photons above or below the band gap energy of a single junction solar cell. This allows us to increase efficiency to as much as 39% for a quadruple junction solar cell. Now, these things can basically be printed onto surfaces, which is really cool. Perovskite cells are as efficient as multi-junction solar cells, but they're much, much cheaper to make, about 1/20th to 1/80th the cost of silicon cells. They can be sprayed onto surfaces, maybe eventually be incorporated into vehicle paint, making the whole surface of a vehicle a solar panel, except the glass. So let's go perovskites. Turns out that the organic layers that are basically spray painted onto a surface, while being very efficient in collecting solar energy, degrade because of that very solar energy. The light breaks down the organic molecules. Other things being worked on at this time include glass. Transparent glass can serve as a solar panel. So this allows us to use glass that encases buildings around the world as solar panels. Now, in 2014, the efficiency was about 1%, which isn't all that good. People working at Michigan State University and the University of Michigan more recently have worked to get that efficiency from around 1% up to 10% as of 2021. Now imagine a future where every window in a large city is capturing, with 10% efficiency, solar power. That's an enormous amount of energy that's just waiting to be gathered. It's wasted by warming up buildings that then need to be air conditioned or bouncing off the window or reflecting into the street. Someday, and I predict someday soon, architects and homeowners will pick and choose the tint they prefer for the glass that's going into the windows of their building or home. Already there are a couple different tints available. There's a greenish hue and a grayish hue available with 60 to 70% transparency, which would be similar to tinted windows in a vehicle. So it's not ideal yet. It's not crystal clear glass, but that's coming. And the way you can harvest light from crystal clear glass is collect the light we can't see. Infrared radiation and ultraviolet radiation, for instance. We can't detect it with our eyes, so it doesn't matter if it's collected and converted into electricity. This brief discussion of solar panels is only scratching the surface of the past, present, and future of solar power. There are numerous efforts using a wide variety of technologies to generate power economically and efficiently. Many other technologies are being developed today. We could spend many months talking about them without ever catching up because the technology is evolving so quickly. Now, I know what you're going to say next, but what about when the sun isn't shining on my solar array? How do I use my popcorn maker? That, my friends, brings us to another wild ride on the battery side of technology, coming up next. Stay tuned.